So to define a Bronsted and Lowry acids and bases. Bronsted and Lowry acid is an acid that contains a hydrogen, and it is capable of giving this hydrogen away to another substance. Bronzed acids, they are arenous acids. They are arenous acids because they have to contain a hydrogen. And in the solution, they release the hydrogen in the solution. So it is any hydrogen containing substance that is capable of donating a proton. This means that they are releasing a hydrogen to the solution. So bronzed and Lowry acids, these release a hydrogen to the solution, and the hydrogen is going to be in terms of H plus. So that acid releases a hydrogen to the solution in terms of H plus. In other words, bronzed and Lowry acids normally loses a hydrogen. Now, bronzed bases, these are arenous bases, and these are any substance that is capable of accepting the hydrogen from the acid. Okay, so the acid releases the hydrogen. The base accepts the hydrogen. Why the base accepts the hydrogen? Because bases, they do have electron-rich site, and this electron-rich site, they can come and take the hydrogen of the acid. Let's have an example. HCl plus water. So if I have these two components in here, this reaction runs by a double replacement reaction. So let's have an example over here. If I'm reacting HCl and water, so these two are my reactants, these two are going to be my product. So whenever you have an acid, always acid reacts with a base. You cannot have a reaction with two acids. So two acids have no reaction, two bases have no reaction. So if you start with an acid, then definitely it needs to react with a base to get to the product. Now, how do I know that my first component is an acid? It needs to start with a hydrogen, you guys. So since it's starting with a hydrogen in there, I do have HCl and I do have water. Now you're going to say, okay, water also starts with a hydrogen. Yeah, water can act as an acid, water can act as a base. But the question is, which one is more acidic than the other? Okay. And to determine which one is more acidic than the other, I need to look and see what is the hydrogen connected to, what element the hydrogen is connected to. By definition, a hydrogen needs to have a partial positive charge. So the hydrogen needs to be connected to an electronegative element. And the more electronegative element you have next to the hydrogen, the more acidic is the hydrogen. Why? Because we measure the acidity by how electron poor the hydrogen is. And we represent the electron poor by partial positive. Because normally hydrogens or acids are electron poor. And the more electron poor they are, the more acidic they are. So if the hydrogen is connected to a very electronegative element, if you look at the direction of the polarization here, the electronegative element simply steals electron from the hydrogen. And the more electronegative it is, the more it steals electron from the hydrogen. So when it steals electron from the hydrogen, this hydrogen will become more partial positive. The more partial positive the hydrogen is, the more acidic it is. So here I do have two types in there, two components that start with a hydrogen. I do have a hydrogen that is connected to a chlorine and the hydrogen that is connected to the oxygen. Because why? Because through the Lewis structure of the water, then this is what you're going to end up having. You're going to have a hydrogen that is connected to the water. So both, they have a direction of polarization in there, where oxygen is also electronegative, causes the water to be, or the hydrogen of the water to be partial positive, and the chlorine is electronegative as well. So this is the chlorine, it is electronegative as well. And this chlorine also causes the hydrogen to be partial positive. Now, the question is, which one of these is more electronegative? Is it the oxygen or the chlorine? This is the pull of electrons, you guys. So I know that electronegativity increases from left to right in a period, right? So this means that chlorine is more electronegative than oxygen. So chlorine pulls more electrons towards itself than the oxygen. It pulls more electrons from the hydrogen. So this hydrogen, I'm expecting it to be more electron deficient, meaning more partial positive, and this is why HCl is more acidic than water. So if the HCl here is the acid, this one is going to be called the Bronsted acid. So it's going to be Bronsted. It's going to be Bronsted and Laurie acid. You can call it the BL acid, the Bronsted and Laurie acid, or Bronsted acid. Then water, definitely it's going to be the Bronsted base. Okay, so that one is going to be the Bronsted and Laurie base in there. So by definition now, I need to locate the partial positive or the acidic site of the Bronsted acid. And the Bronsted acid by definition needs to start with a hydrogen. So I know this hydrogen is going to be my acid. Now for the Bronsted base needs to be electron rich. So here what do you have? You have a reaction between an electron rich site and an electron poor site. The electron poor site is the hydrogen, always from the acid. And the electron rich site from the Bronsted base is the lone pairs on the central atom. So over here, I do have my water. Water has two lone pairs in there. So I look and see, okay, no, where is my electron rich site in here? I know that these two hydrogens, they lack electrons because this is partial positive. This hydrogen over here is partial positive because again, your direction of polarization is towards the oxygen. So my electron rich site is actually the oxygen because the oxygen is stealing electrons from both hydrogens. So now this is going to be my site in there that I'm going to say, okay, this is going to be my basic site. Okay, so that oxygen is going to be my basic site for the Bronsted base. So bases are known for their electron rich site. Acids are known for their electron poor hydrogen. The more electron poor the hydrogen is, the stronger is the acid. Okay, so how does the reaction goes in here? The reaction goes by bases. So from their electron rich site, they always take the acidic hydrogen. So now this oxygen in there is going to lose, it's going to use one of its lone pairs in order to make a bond with the hydrogen. And then your product over here is going to be H3O plus. So let's go ahead and draw that. So what did we do over here? That base, which was water, took the hydrogen from the acid. And this is the definition of a Bronsted and Laurie bases. Bases from their basic site, they accept a hydrogen from the acid. Bronsted and Laurie acids, they lose a hydrogen to the base. So it's going to be give and take. Okay, so the acid gives a hydrogen, the base takes the hydrogen. And what you create over here is what we know. This is the acid that was added. What we create in here is what is known as a conjugate acid and a conjugate base. So you're going to end up getting a conjugate acid and a conjugate base. And this is the definition, okay? Bronsted acids, they lose a hydrogen and they become Bronsted acids, they become conjugate bases. So you go from the acid to the base. So the Bronsted acid, they become conjugate bases, and the Bronsted bases, they take a hydrogen from the acid and they become conjugate acids. So your product here is going to be a conjugate acid and a conjugate base. And here I'm just comparing the acidity of hydrogens that are connected to carbon to nitrogen, to oxygen, and to a halogen. So let's keep the same trend in here. So you do have a hydrogen in there. Okay. So if the hydrogen is connected to chlorine, chlorine is the most electronegative element. So we said that chlorine is going to pull out the most electrons from the hydrogen to make it the more partial positive. Oxygen pulls out also electrons from the hydrogen. It's also partial positive, but not as electron deficient as the hydrogen that is connected to the chlorine. So this is why I'm going to consider this hydrogen to be the most acidic, and HCl is going to be the strongest acid among all of these. When hydrogen is connected to nitrogen, nitrogen is not very electronegative. So this hydrogen is not going to be so much acidic compared to the one that is connected to the oxygen. And definitely carbon is not electronegative. So carbon, it's not very electronegative. So if you look at the electronegativity table for the carbon, it's almost the same electronegativity between the carbon and the hydrogen, with the slightly carbon being slightly more electronegative than hydrogen. So I'm expecting that this hydrogen here is not acidic. Okay, it is not acidic. Guys, acids are known for their acidic hydrogen. Bases are known for their basic site. So you look, where are your lone pairs, and this is going to be your base. And always go by the rule, bases take acidic hydrogens. Your product is going to be a conjugate acid and a conjugate base. The bronzed and lauric acid changes into a conjugate base, and the bronzed base changes into a conjugate acid. Also, another thing to know whenever you're looking at the product, a positive charge is an indication of acidity. So if you have a plus charge, this indicates that it is acidic, and a negative charge indicates that it is basic. Okay, so a negative charge indicates that it is basic, and this is why I know that chlorine definitely needs to be a base. And in my products, the name of the base now is a conjugate base. It's not a base. The base is in the reactants. The product is going to be a conjugate base. Okay, and the conjugate base results when the acid loses its hydrogen. The conjugate acid forms whenever the base takes the acidic hydrogen. Let's have another example. I do have nitric acid, nitrous acid. I'm sorry. This is nitrous acid. So this is nitrous acid. It's an acid by itself. Why it's an acid by itself, you guys? Because it started with a hydrogen in there. And I do have my water. So since I started with an acid, definitely I cannot have two acids next to each other. So one of them is going to be the acid, definitely the other is going to be a base. So I'm just going to go ahead and label the basic site. And I would go by this definition that the reactions always start from, so this one's going to be the bronzed base, and this one is going to be the bronzed acid. Okay, so always the reaction starts from the base. Put it as a note that reaction starts from the base. Why the reaction starts from the base? Because the base has electrons to give, to take this hydrogen that is lacking electrons. So always you start your reaction from the electron-rich site, and that electron-rich site will donate its electrons to make a bond with the electron-poor site. By going by the definition that bases, they take the acidic hydrogen. So over here, the base is going to come take this acidic hydrogen. So water is going to turn into H3O plus. I used one of the lone pairs. So one of the lone pairs, I used this lone pair here. So one of the lone pairs is going to make a bond, covalent bond between the oxygen and the hydrogen. The other lone pair will stay. Now oxygen is positive charge. And you guys, you know oxygen is plus charge. Look at your formal charge table, please. Oxygen has 3 bonds and the lone pair, so it's a plus a charge. And then the leftover from the acid is the NO2 negative. This is a polyatom. You can look at the polyatomic table to know it's a charge. It is a negative charge. Actually, the hydrogen here is going to dissociate. It's going to be H plus and the NO2 minus. So I know that this guy is going to be in negative charge as well. And then we said that the bases will turn into conjugate acids. So that is going to be a conjugate acid. And the acids are going to turn into conjugate bases. Another way also to know this is by looking at the charges. We said that negative charge is an indication of what? Of a base. Okay, so that is going to be my conjugate base. And positive charges, these are indications of acids in there. So this one is going to be an acid, so it's going to be acidic. This one is going to be basic, so let's put it as acidic and basic rather than an acid and a base, because acids and bases are in the reactants products. You get conjugate acids and conjugate bases. Okay, this hydrogen over here is not connected to a nitrogen. So you might tell me, okay, this hydrogen is connected to a nitrogen, so why water is not acidic than this hydrogen over here, since oxygen is more electronegative than nitrogen? Well, go ahead and draw the Lewis structure of the nitrous acid. And the Lewis structure for the nitrous acid, after you go ahead and you figure out your valence electrons and whatever, distribute your electrons in there. We said that hydrogen can never be a central atom. So your central atom here is going to be the nitrogen. Okay. Around the nitrogen, we said when you draw your Lewis structure, you start with your central atom and you distribute everything except the hydrogen, because hydrogen can never be in the middle and hydrogen can never be in the center. So definitely the hydrogen now will be connected to one of these oxygens in there. I do have a 0 charge for the nitrous acid. So definitely this nitrogen is going to be positive and this oxygen is going to be negative, so that to balance the 0 charge of the nitrous acid. So you can see here that the hydrogen is connected to the oxygen, and here the hydrogen is connected to the oxygen, but this one here is going to be more oxygens next to this hydrogen. So they're going to pull more electrons from this hydrogen and make this hydrogen more partial positive. Because it's more partial positive, this is why it is going to be acidic, okay, compared to the water that is now a base. So again, from the acid, you choose the hydrogen. From the base, you are going to choose the basic site, which is the electron-rich site. It's the lone pair site. Let's have another example. So we have ammonia, and we do have water. Okay. So what do we have here? We have water. Let's go ahead and draw the Lewis structure of the water, and let's draw the Lewis structure of ammonia just to see the hydrogen and what it is connected to. Okay, so this is the Lewis structure of both. So here we do have 2 types of hydrogens. A hydrogen connected to the oxygen and the hydrogen connected to the nitrogen. Which one is more electronegative? It is the oxygen that is more electronegative. So because the oxygen is more electronegative, it's going to pull more electrons towards itself, leaving the hydrogen more partial positive. So more electron deficient. And because the hydrogen is more electron deficient than that of the nitrogen, this hydrogen over here, yeah, there is a direction of polarization towards the nitrogen, but this one is going to be less electron deficient. And because it is less electron deficient, deficient in there, because it's less electron deficient, I cannot say that this hydrogen is more acidic. This hydrogen is less acidic. So this means that water now, it's going to be my Bronsted acid. So water is going to be my acid. So this one is going to be my Bronsted acid. Okay. So water is going to be my Bronsted acid. There is a line on the O there. It's how it's written, Bronsted acid. And ammonia from the nitrogen. So the hydrogen, one of these hydrogens, either the one to the right or the one to the left, are acidic. And then the nitrogen, which is the base now, So this is going to be my base. So if it's my base, I no longer can choose the hydrogen in there. I already chose it for the acid. So the base needs to have a basic site, which is the electron-rich site. And then I go by the definition that, guys, bases, because the reaction starts from the base. So bases will come and take the acidic hydrogen. Okay, so now my product is going to be NH4 plus, because your product here is going to look like this. I already had ammonia as my base. The lone pairs of the ammonia will come and take that acidic hydrogen of the water, and we're going to end up having NH4 plus. So the base, so we're going to call this a Bronsted base. So that the Bronsted base is going to turn into a conjugate acid. Again, it is positive, so it is acidic. And the leftover from the Bronsted acid is OH. So now that is going to dissociate into an OH minus, and that is going to be my conjugate base in there. Okay, so that is going to be my conjugate base, because it does have also a negative charge. Remember, your solution over here is basic because of the OH. So that's, if you have OH in your product, then this tells you that your solution is basic. Here, I do have H3O plus. H3O plus, we're going to call this hydronium ion. This is called hydronium ion. Let's write it right. So this is hydronium ion. And in most of the cases, hydronium ion is represented by an H plus. So if I look at the identity of my solution, I can see that my solution is acidic because of the hydronium ion. So the hydronium ion, the H3O plus, is the same as H plus in there. So its presence is going to tell me that my solution is acidic. Okay? The presence of the OH minus in the product is going to tell me that my solution is basic. Same thing over there. The presence of the H3O plus tells me that my solution is acidic. This means that this one is a strong acid. Okay. This one, my solution is acidic. This means that the nitrous acid is a strong acid. Ammonia, my solution is going to be basic. So this means that ammonia is going to be a strong base. Now, the term conjugate acids and conjugate bases. So we mentioned that you start with acids and bases. This is on the reactant side. And then you get your conjugate acid and your conjugate base. So the term conjugate acid and conjugate bases, this is strictly limited to the products, not the reactants, products. So how can conjugate acids and conjugate bases form? So conjugate acids, they are simply formed whenever the base takes the hydrogen. And conjugate bases, they are formed whenever the acid loses its hydrogen, it becomes a conjugate base. So let's say, for example, if I give you a series of compounds, okay, all of these you can easily see that they start with a hydrogen, right? So if they start with a hydrogen, then I'm starting with an acid in there. So all of those, they start with a hydrogen. This is the definition of Bronsted and Lowry acids, all of them. All of them are Bronsted and Lowry acids, same thing as Arrhenius acids. Okay, so I ask you, starting with these acids, change them into their conjugate bases. So to change each one of those into their conjugate base, all what you need to do is just allow the hydrogen to do its job, and or allow the acid to do its job and lose a hydrogen. Just lose a hydrogen. So that's why we have an H plus in there. This means that the acid is losing a hydrogen. So when the H3O plus loses a hydrogen, that is going to become water. It's going to become water. So what is water now? Water is going to be the conjugate base of the H3O plus acid. Okay? H2SO4 is going to lose a hydrogen. So when it loses a hydrogen, that is going to become an HSO4 minus. And that one is going to be the conjugate base of the H2SO4. You can look at the polyatomic table for the charges of these conjugate bases. So that is going to be an HSO4 minus in there. Same thing for the H3PO4. If it loses just one of the hydrogens, then it's going to become an H2 and it's a PO4 and it is going to be a 2 minus. HNO3, that is going to be, it loses a hydrogen, right? So that is going to be an NO3 and it is A minus. You can find these charges in the polyatomic table. Acetic acid. This is an acid that gives the vinegar its smell. This is how it is written. It's called an acetic acid. The acetic acid has an acidic hydrogen because if I draw its Lewis structure, I'm just going to go ahead and draw the Lewis structure there. It's three hydrogens that are connected to the carbon. So I'm just going to write them as a CH3 like this. And then you have the C and then OO and then H. So what is that? It's a C double bond O and it's an O that is connected to the hydrogen. So you can easily see that this hydrogen there is this hydrogen over here. And this hydrogen is going to be an acidic hydrogen. See, vinegar is edible, right? So acetic acid cannot be a strong acid. It has to be a weak acid because you cannot consume a strong acid. So vinegar, which is acetic acid, is a weak acid. It does. So vinegar loses its hydrogen in there, but not completely though, because you are going to end up having a conjugate base. So it's going to be a C double bond O. This is an O minus. This is going to be the conjugate base in there. Now, when acetic acid dissociate in water, as I draw the dissociation equation there. So when acetic acid, it does dissociate in water. So if this is aqueous, it's going to dissociate into H plus and its conjugate base in there. Okay, these are the basic ions, but some of it is going to remain undissociated. So plus undissociated CH3COOH aqueous in there. And this tells me that this is a weak acid because not all the acid dissociate into H plus. Some of the acid remain in a form of an undissociated acid. This is a hydrogen. Okay, but the point is, this is aqueous. But the point is, whenever you start with an acid, you're asked to draw its conjugate base. Just allow the acid to lose the hydrogen, the acidic hydrogen, and turn this into its individual ion. If you start with a base, so all of these are examples of bases. Remember what I said. A negative charge is a form of a base. A negative charge is a base in there. Water doesn't have a negative charge. It does have a lone pair in there. Nitrogen does have a lone pair. So if you have an electron-rich site, the negative charge is an indication that there is an electron-rich site, because if you look at the Lewis structure for the NO2, so you do have the oxygen in there. This is where the negative charge is. The negative charge is where the lone pairs are. So this is going to be our electron-rich site. This is the electron-rich site where it's going to take the acid. So at the end, the acid is going to end up bonding with this hydrogen over here. So my product is going to be over here, an H. It's going to be an HNO2. Or you can draw it as a hydrogen, oxygen, and then an N double bond O. So this is it. This is how you draw HNO and O2 in there. Okay. Water again, all of these are electron rich sites. So at the end, you need a base with an electron rich site over here. So electron rich site, and then you have your bromine in there. As long as you find a lone pair, then this is going to be your electron rich site. So now you're going to allow the hydrogen to bond to this electron rich site. So now your hydrogen is going to bond over here. Add the hydrogen is going to bond here, and your product is going to be an H3O plus. Or you can write it as, if it's easier for you, you're allowing the hydrogen to bond to the electron rich site, so it's going to bond to the oxygen. Same thing over here, it's going to be an H4 plus, or you can write it in its Lewis structure there, allowing the hydrogen to bond to the electron rich site. Please make sure to follow the formula charges of the oxygens and the nitrogens whenever you are writing your conjugate acids. Over here, my electron-rich site is the oxygen. So this is an OH minus, it is a base. I want to change it into its conjugate acid. So I'm just going to add a hydrogen. So the OH now is going to turn into water. It's going to turn into water. So what you did is you allowed the electron-rich site, this is the electron-rich site, to take a hydrogen from the acid. Bromine, again, bromine is going to take the hydrogen from the acid. This is the electron-rich site. So what I'm going to end up is hydrogen bromide, or another name for it is a hydrobromic acid. These are binary acids. HS minus is going to be my base. This is going to be my conjugate base. You can simply see the lone pairs in there. So where is your electron-rich site? It's the sulfur. The sulfur. This is the electron-rich site. So since this one is a base, the base will take an acidic hydrogen, and I'm going to end up getting H2S, or you can draw it in its lowest structure in there. Here you go. I used just one lone pair, so I still have two more. And this is called hydrosulfuric acid. H2S is a hydrosulfuric acid. These are binary acids.